absorbed in this. But now this is also has to be removed. You have introduced in the water. So because here you have iron oxide, you put one magnet here. All this thing actually get attracted here, and it is removed, and you are left with clean water. So this is what something interesting is done. But this is, see, the challenge is that we are doing these experiments at lab level in a beaker and test tube. When we go to the industry, they talk of, we went to the industries to discuss all those things. They said they are very good, very interesting thing. Can you do it for 50 million liter a day? That's the challenge. I cannot do it. So first I have to scale up. And scaling is not done from test tube to 50 million liter a day. First you have to do a middle level. So do for 10,000 liters. And doing for 10,000 liter requires much more money than doing the test tube. So we are stuck there. So somebody has to fund that, and then we successful in that. Then we go to the actual industry level. So these are the real problems I am telling you. In security and defense, there are a lot of things in where the nano is playing role, and these are the things. Night imaging device, the tank moving in night, and with the IR devices you can actually view it, but then you can improve the imaging by using the nanomaterials. And then heat-seeking missiles. That means there is a missile, whenever it is actually, there are some concepts where the exhaust of the enemy plane is always hot. So the missile is having something which is seeking that heat. Again, it is based on IR detectors. And there also nano is playing a role. Bulletproof jackets. So to save the soldiers, you have to have bulletproof jackets. And nano, in certain form, in certain cases, it's more harder than other materials. So this plays a big role. Anti-corrosion materials for submarine and warships. Because this is a huge cost. If this is rusting from bottom, then you can improve the life by having anti-corrosion coatings. So this kind of paints are being developed, which are actually having super hydrophobic surface. So it doesn't actually contact in the water so much, and it helps. There are explosive detectors which are actually utilizing this nanotechnology. So well, I have given you a glimpse of different kind of things related to the society. Some things we are doing, we cannot do everything. So you are all there to look up the problems and do the things. And I will just say about our institute that we are 22 faculty, 122 UG students, 26 PhD students. We have some technology transfer given to some industry from the patent. They bought the patent, and 200 publications, and we have a lot of projects going on. And so research support at our institute, we are having currently 17 projects covering around 480 lakhs from different agencies, DST, DBT. PIRAC is something which actually demand the product, and then they are not interested in research papers. They want a product. So some of the things I showed there, they are basically nanobiosensors. We are close to making a product. Then the Department of Atomic Energy, DRDO, we have some projects from them. And NASF, National Agriculture Science Fund, ICMR, Indian Council of Medical Research, UCDACR, UK Air India, UK-India collaboration is there. So like this we have many things going on, and this will come or? Yes. I think I am already at the end of it. So basic idea was to tell you that the role of nanotechnology is not in a single field. It is covering all sciences, all branches of science, so physics, chemistry, biology, and then engineering. I showed one example of engineering, but then there are many more examples where it is playing a big role. And it has a very special field which has a connectivity with different branches of science. You talk of any science, it has a connectivity. I mentioned the physics, chemistry, biology, the basic sciences, forensic sciences, agriculture sciences. In agriculture there is a lot to be done for detection of pesticide in the soil, detection of pesticide which are going in the plants which you eat, detection of pesticide in the food. The nanotechnology, nanobiosensor are playing big role. There is a big future for that, and it is to help the society only. Okay, and they say it has a connectivity with all branches of engineering, mechanical engineering, electronics engineering, electrical engineering. You can question me that where, how, I can answer that, but then I just wanted to throw the ideas, and then you have to ask the questions and ask me. So in the end, I had put that collaborators we had there. So I think we can utilize this time for the questions. So I was almost at the end of what I wanted to talk. So I would like to invite the questions from the students.
Any questions?
I'm not a student, but
Yes.
just one thing.
Yeah.
You have given a nice overview of the nanotechnology, the various fields of it. Can you tell me what are the commercial aspects of these defense applications in developed countries? Of course, we have
Yeah.
but what about the developed countries?
In developed country, if we talk of defense, then nobody opens up. Nobody will tell that what they are doing. In the same way, here also a lot of things are going on. We also have a project from DRDO, but we cannot talk that what we are doing. So there are certain protocols and this we have to go there. But never the matter, what we talked, they are there, already there. But they will not disclose that which kind of material.
No, not that. About the commercial aspect. That's what I am saying.
Okay.
They are
In commercial aspect,
being developed and
I
tell you what they are
Right.
doing. But about the commercial aspects of this.
Sure. I got your point. So in commercial aspect, when we talk, then it could be any field, not necessarily defense, because defense will not open up, as I said. For example, a drug, I didn't talk about this drug delivery and all those things, which is very important field as such. And this in nanoform, the things are more effective because of more surface area. Okay, this is very clear, right? And in higher surface area, you can have more functional groups. A material cannot be functional at a bigger scale, but may become functional at a nano scale. There are electronic configuration and all those things, they are responsible for that. But then, if that is so, then one example, as he said, is there are actually drugs which are used in cancer therapy. One injection, chemotherapy injection, typically costs 20 to 30,000. But now there is a nano drug, which is actually 10 times costlier. It is 2 lakhs in one injection. The cost is processing cost. So this is one example. This is already commercial. It is not that it is not there. See, in health sector, there are a lot of nano biosensors are there. I talked of one milk adulteration kit, which was actually transferred to the company. This has a nanomaterials inside. So there are a lot of things which are there, which are nanomaterials commercially. But see, this is something. Often this kind of things are asked by students also. What about the nano industry? The nano is something which is a add-on value to a product. Not that you can have a product of nano. So for example, I gave the example of a car in engine. In automobile industry, there is a role there. Okay, that you are taking the heat on the engine. Okay, then there could be some materials which are there are some cycle industries, they have approached us. They wanted that the cover on the what is that called, mud guard, it should have hydrophobicity so that it doesn't get dirty. So they are also getting smarter, you know. So a hydrophobic surface is always a self-cleaning surface, like a lotus plant. So they are intelligent, so they come to us, can you do this? So but this is to be done at large scale, not in the lab. This is the thing. So the challenge is to transform from lab scale to the large scale. Yeah. So questions, any more questions?
This is a very wonderful line, Johnson. Just one question. In one of the slides, you mentioned that using ion beam mixing technology, we can form alloys.
Yes. Compounds.
Yes. So the question is that using sputtering or pulse laser deposition, by using many targets at a time, we can do this alloying kind of thing.
Compound formation, yes.
And that can also be employed using sputtering. That can also be employed for commercial applications.
Yes.
My question is how ion beam mixing technology is better or worse in comparison to sputtering or pulse laser?
Okay. Academics wise, if I go, I cannot compare the technologies because ion beam technology is always very expensive. The pulse laser deposition, any other thin film deposition tools are ready for, they can be industrialized.
Yes.
Scale up is easy, right?
Yes.
But from academics point of view, if I try to do, let's say, cobalt and antimony by co-deposition, by pulse laser or RF or any other method, then they may not form a compound, may not.
Okay.
There will be COSB, COSB2, COSB3.
Okay.
Okay, maybe you are able to make some of them, but selectively I am showing in ion beam processing, I am getting COSB3 at certain conditions, okay, which is not possible by PRD or by other techniques. That's the important. The reason behind is, when you are depositing things, they are actually coming to the vapor space and then get condensed, whether it is sputtering or whatever. Their energy of the atoms is thermal energies, okay. So it will be fraction of electron volts. But here, with the ion beam, when you are depositing energy, it's a huge energy. It can actually change the things, which is quite different from the other process.
Okay. Thank you.
Yeah.
Any further questions? Maybe at tea time. Further questions?
Yeah,
maybe at
please.
tea. Thank you.
Thank you.
Thank you, sir. May I now request our distinguished guest on the dais to kindly read the abstract booklet for the conference. Thank you all. I request Dr. Ashok Gupta, Honorable Vice Chancellor, IIS University, to present a token of our fond remembrance and gratitude to our keynote speaker, Dr. D.K. Awasthi. Thank you, sir. I now invite Dr. V.P. Bhargav, Head, Department of Physics and convener of the conference, to kindly deliver a formal vote of thanks.
Namaskar. Professor D.K. Awasthi, keynote speaker at the inaugural session. Dr. Ashok Gupta, Honorable Vice Chancellor. Professor K. Sharma, Advisor, IIS University and Conference Chairperson. Dr. Rakhi Gupta, Registrar, IIS University. Professor Pradeep Bhatnagar, Dean Faculty of Science. All the esteemed invited speakers, participating delegates and guests in the audience. It is my proud privilege to propose a formal vote of thanks on behalf of IIS University, Jaipur, at the inaugural ceremony of two-day National Conference on Recent Trends in Material Science and Technology. The conference has been planned keeping in mind the need for developing materials for various applications, including optical, thermal, mechanical and energy-related applications. I am confident that these 2 days will provide an ample opportunity to one and all to exchange their views and research ideas on the latest development and future trends in the field of material science and synthesis, characterization and technological applications of nanomaterials. I would like to express my deep gratitude to Professor D.K. Awasthi for so very kindly acceding to the request to deliver the keynote address. Thank you, sir, for your presence and insights. Your address, sir, has set the tone for deliberations that are to take place over these 2 days. I am thankful to all the invited speakers for taking time out of their busy schedule to be here and consenting to speak on contemporary topics in the field of material science and nanotechnology. Thanks are also due to all academicians, delegates and students who have come from far and wide to attend the conference. I sincerely hope that your inputs and interaction during the course of this conference will make new contributions to the field and will be of immense value in times to come. My thanks are due to Dr. Ashok Gupta, Honorable Vice Chancellor and Conference Patron, for his unstinted support and invaluable guidance throughout, which has given this two-day event its present shape. I am also grateful to Professor Rakhi Gupta, Registrar, for her meticulous planning and attention to details which has helped us immensely in organizing this event. I also thank Professor K.S. Sharma, advisor, and Professor Pradeep Bhatnagar, Dean Faculty of Science, and Professor Y.K. Vijay, Director VGU, for guiding us at every step and extending their support. I also convey my sincere thanks to Dr. Ritu Jain, Organizing Secretary of the conference, for her sincere efforts and hard work. I would also like to thank all the faculty members, not from the Department of Physics, but from other departments as well, student volunteers, and the technical and support staff towards the smooth conduct of this conference. Lastly, I thank all the media persons whose ample coverage of the conference will bring this contemporary issue closer to the public interest and notice. With the hope that this conference will accomplish all its objectives, I wish it all the best. Thank you once again.
Thank you, ma'am. With this, we come to the end of the inaugural session of the conference. I request you all to kindly remain seated till the dignitaries have left the hall. And Defense, and has published more than 125 research papers. A proud recipient of Sir J.C. Bose Best Paper Award from ITEE, he is a member of various societies like IEEE, IETE, IBS, TSSI, VEDA, IFTA, and chairman member of various advisory review committees of different organizations like DRDO, DAE, ISRO, CSIR, IIT BHU, to name a few. A co-chairman of Core Group on State SMT-oriented demonstration projects of DSC for 3 years, he has been actively associated with the activities of National Council of Science Museums for the last 5 years, and in present, Chairman of the Research Advisory Board of NCPM. We welcome you, sir. I now request Professor K.S. Sharma, Conference Director, to please extend your welcome to our distinguished guest. Professor Y.K. Vijay, the chairperson for the technical section of this conference. Dr. Arun Pratap.
Sir. Sir की बात सुनो. आजो.
And Dr. S.N. Joshi. Thank you, sir. I now request Professor Y.K. Vijay to kindly take over for the subsequent proceedings.
Okay, thank you so much. And good morning to you all again. Good noon, in fact, but anyway, whenever we start our day, that's the morning. And I'm happy to share with you that this morning we had a wonderful start by Dr. Awasthi on nanotechnology and its application for the society. And now we shall have another very important talks on quasicrystals and nanocrystals by Professor Arun Pratap and the microwave devices by Professor Joshi. So I welcome you to pay attention. I like to share with you that we are delayed in our high tea, so probably we will stick to our time to say 25 minutes and give 5 minutes for question hour session. So within half an hour we are through with the invited talks. Then certainly these 5 oral presentations I like to share with you that we give them about 6 minutes time for presentation and 2 minutes for discussion. Okay, so that we will be ready for our lunch and enjoy the lunch. Okay, so enjoy the session I invite Professor Arun Pratap, please.
Yeah, very nice words. And giving the title of the topic which I'm going to talk about. At the outset, I'm thankful to Professor Vijay for inviting me for this conference, and to the organizers at this IIS University. It's very heartening to see so many students, and among those young students, it's also very heartening to see my former student, Ritu Jain, to whom I taught in way back, as she remembered, in 1995 probably. 94, 95, I think 95, in BSc Physics Honours in Maharani College. So nothing as heartening to have your student in the audience. So this is my pleasure to be here, and I am also thankful to the administration of this university, the Vice Chancellor, then Professor K.S. Sharma, for giving cordial welcome. Well, what I am going to talk about is about the nanocrystals, and how did this field originate? Then nanocrystals, what are their specialties like? Most of you might be knowing the basic things, that the nanocrystals, the size of the crystals is of the order of 10⁻⁹ nanometers. So due to this, what happens that
-9 meter.
Yeah, -9 meters. Therefore, it's -9. So many students think that, well, is it smaller than atom? It's not. An atom is still indivisible. So it's two atoms. And due to this small size, what happens that you have very large surface area compared to the volume. And there are many properties, functional properties, like catalytic properties, gas absorption, and many other properties which depend on surface area. Therefore, these nanocrystalline materials, they are very useful for from application point of view. Then, if you move over to the nanocrystals, and you might have heard that these nanocrystals, they kill bacteria, and they have that way antimicrobial action. In the same way, there are certain systems which have the forbidden 5-fold symmetry. Even now in the textbook, you will find that the 5-fold symmetry is forbidden. You have 2-fold, 3-fold, then 4-fold and 6-fold. But 5-fold symmetry is forbidden. But with the advent of few systems, we have 5-fold symmetry, which is possible, and it was shown by Dan Sechtman of Israel in 1984-85 that we can have 5-fold symmetry. So if you can have 5-fold symmetry, you can also have those crystals in the form of nano. And if you have nano quasi-crystals, there are many viruses which have quasi-crystalline structure with 5-fold symmetry, and as regards their size, the size is in the nano range. So just like the nanocrystals are used to kill bacteria, nano quasi-crystals can be used to combat viruses. And from application point of view, this is a very open field. So anybody, any new student can think of doing this, and perhaps there is one issue I thought, but perhaps I didn't get time. any new researcher can think of getting collaboration from National Institute of Virology. It's a very sensitive issue of doing research on medical field or on live things, but you can think of that. And one example of this quasi-crystalline virus is the polio virus. Like that, there are many viruses which are quasi-crystalline in structure. So that is one field. So I will try to just start a few things from Feynman, because he is supposed to be the father of nanocrystalline field or nanocrystalline materials. Because way back in 5960, he had given a statement that there is a plenty of room at the bottom. I will come to that. And incidentally, I don't say that I have contributed much. I have done some work which I will try to share with you. But I was born in 1959 when he had given this statement. You can appreciate that how much time has passed and we have still not come to real application. We have of course come to a few things, but like the drug delivery in pharmaceutical applications, targeted drug delivery. But there are many fields in which we have still to do a lot of work as regards the application. So, first slide. Yeah. So this is the outline of my work. You will kindly excuse me, I have some eyesight problem because of cataract. But so mostly I will speak extempore. Slides, you can just go through it or you can see it. So this will be the outline of my presentation. That what Feynman said, that there is plenty of room at the bottom, and then I will talk about this nanomaterials, and then this quasi-crystals, nano-quasi-crystals, and then their applications or nanomaterials in metallic glasses. My field has been metallic glasses which are amorphous in nature by controlled crystallization, because they are amorphous materials, but if you do controlled crystallization of these metallic glasses, you can have nanophage, or you may not have pure single phase nano, but you can have a mixed phase, which will be basically a kind of composite of nanocrystalline material and crystalline material, or nano-crystalline material and amorphous phase. It has certain advantages. These composites or the two-phase or more than two-phase systems, they have their own advantages. They have very good mechanical properties, mechanical strength and other things. So it's a kind of blessing in disguise to get a composite in the process. But the root here will be crystallization of the amorphous phase, or by controlled heating. In a way, controlled heating means heating it very fast, so that if they crystallize, the crystals are very small in size and in the nano range. Otherwise, what will happen if you heat it slowly, then they get a time, the crystals get time to grow. So when they grow, you have the usual crystalline materials. So basically, the term which is used is called annealing. It's just like if you set a target temperature for a system to heat, you set your furnace at that particular temperature, and then introduce the material inside it, of course controlled atmosphere, or you seal it in a quartz ample with vacuum, so that it doesn't oxidize, because most of the systems I will be talking about, they are prone to oxidation. They are metallic systems, so you have to do controlled annealing, and you take it up to that target temperature. Of course, you decide the temperature strategically, and then by choosing that temperature, you put it inside the furnace for a fixed number of times, 5 minutes, 10 minutes, and then you observe the crystals, mostly in transmission electron microscope or XRD if the sample is bigger in size. Most of the samples which I will be talking about, they will not be bigger in size, So it is transmission electron microscope study which will be presented, so that you have feel of how to get this nanocrystalline phase. Next one. Yeah. Well, so Richard Feynman said that there is plenty of room at the bottom. Now, when he made this statement, then nobody actually has put a lot of concern on that. And basically, when he said that, bottom means he means dimension wise. So if you have a smaller materials with nanocrystalline structure or the crystals in the range of nanometers, then lot of exotic properties are observed. So what are those exotic properties? We will also discuss about that. And after that, what is the scenario right now? That also we'll see next one. Well, so if you talk about these materials, there are lot of scope, and if you talk about the systems, next one. Yeah. Okay. So if you talk about the or you take the lesson from Feynman's lecture, then you can see that there are a lot of applications, lot of materials which can be used. Like you have sensors, you have many other materials which can be used for application, and they are in the nanocrystalline range. Next one. Yeah. So here also put a challenge kind of thing. He put a kind of award that if you can have a very small electric motor, he put an award of $1,000, and if it can be controlled from outside, he put a kind of price of $1,000. Why it is required? Because if you talk about these computers, you must have seen the miniaturization of computers when the computers in the old age used to occupy kind of a room. Now you have tabletops. Now you can have even this wristwatches, in the form of wristwatches, you can have your personal computer. How? Because the components can be very small. If the components are very small, then they will occupy little space, and at the same time the expenditure on their manufacturing will also be less. What is the difficulty? The difficulty is that it is very difficult, or it's many times you find it very difficult to manipulate it. If there is any problem in any part, how to correct it? For that you have to have these microscopes which can visualize it. So basically, looking at the dream of Feynman, now the definitions have changed, and one talks about microscopes. With microscopes, with higher magnifying power and resolution at the same time, you can see small things, and it is the cost of this magnifying power and resolution that a microscope, the cost goes up. So microscope was used for looking at the microscopic objects, and you know what is a microscopic object? It is the size goes in the range of 10 to the power minus 6, right? But if it is the size is 10 to the power minus 9, can we have, and there is a development in that area also, I am not going into the details of that, you can check it, that you can have a microscope, in place of microscope, you can have a nanoscope. You can have a machine from which you can look at this nanoscopic or nanometric materials. So can we have an instrument similar to microscope with which we can see the nanometric particles, nanometric materials? In fact, you know that without microscope you cannot see the microscopic materials itself. So it's again very difficult. It is still in developmental stage that we can have, although a lot of work is going on in that area, still it has not come into the commercial use so far, and nobody has a nanoscope, right? Next one. So the problem there is that the state of art is that if you can have a nanoscope, the components have to be very small, and the size will be very small. That is the advantage. But as you know, if you talk about even wristwatch, if you have a wall clock, its cost is less, although the parts are bigger. Material going into them is bigger, is more. But if you talk about a small wristwatch, a beautiful, a small, cute wristwatch, it costs you more. Just because you have not to be precise only, but you have to, if there is anything goes wrong, then you go to the person concerned and show it to him, and they will correct it, but then the cost goes up. Like that, the manufacturing cost also goes up. Therefore, he also made another challenge. He gave another challenge of writing the entire book of encyclopedia on a pin head. So is it possible to do that? If it is so, and nowadays with the advances going on in the area of nanotechnology, it is becoming possible, and somebody can come out with these things and from application point of view, and can get who knows, Nobel Prize. Next one. Yeah, these are some of the factors which I thought it is customary to show you, which we show to our either graduate students or MSc students of nanotechnology, that how to get an idea about the site. So you can see that if you talk about a person, you can see the figure. He is, what is his height? Normal height, his height is 10 to the power 0, let's see. So 10 to the power 0 is nothing but 1 meter, which if you talk in terms of meter, and 1 meter will not be too high. So he's not a very tall person, but it has become a fashion. With the advent of nanotechnology, it has become a fashion to talk in terms of 10 raised to power. And as pointed out by Professor Vijay right in the beginning, I said perhaps 10 to the power 9, but it is 10 to the power minus 9. So now, starting from 10 to the power 0, you can see the different parts or different materials of different size. You can see that when we can go from that 1 meter to the viruses. You can see bacteria also, and you can see the size of the eyeballs and other things. So we always talk in terms of, or we have started talking in terms of 10 to the power. So 10 to the power minus 9, if you talk about viruses, or you talk about this DNA, right? So you can see that these viruses, their size is in the range of nanometers. So basically, why do we require these materials which are nanometer in size? Because we have to deal with all kinds of materials, including the viruses or including the bacteria, right? Next one. Yeah. So you can have these nanometric materials. Either you can have, if any material, normal material, any material you take, it's a 3-dimensional or bulk material. So in all 3 directions, X, Y and Z, the size is quite substantial and you can see it. So that's a very bulk material. But you can reduce the size along 1 dimensions, let us say X direction, and rest 2 directions you have the normal size. So you can have and in that particular direction you can reduce the size up to some few nanometers. Then it's a 1-dimensional nanometric material. If you can reduce the size in 2 dimensions, it's a 2-dimensional nanomaterial, and if you can reduce the size in all three directions, then you can have three-dimensional material. We also call it quantum dot, because classical dot anyway we know. If we put something, some mass to a point, if we take a chalk and put it just point on the blackboard, it's although it appears to you that it's maybe two-dimensional, but there is some third dimension also, and they are substantial. Therefore, it's a dot, but classical dot. But if you reduce the size to nanometer in all three directions, we call it quantum dot, because quantum effects start playing. And what happens, that I have not put into the slides, but there is an effect called the energy quantization. So in that particular direction, there is some additional kinetic energy which is developed, and that gives a lot of exotic properties. So that is called quantum confinement. So if if you reduce it in one direction, you will have quantum confinement along that direction, and due to that you will have so many exotic properties. So you can have one-dimensional, two-dimensional and three-dimensional nanomaterials. The three-dimensional nanomaterials are most extensively used as quantum dots. Next one.
Professor Arun Kumar.
Yes, sir.
May I request you to sum up in 5 minutes?
Is it?
Yeah.
Okay, sir. Okay, go ahead then. Well, just a minute. So, again, when we come to this quantum dots, you will find that depending on the size of the material, you have different colors. You can see that the different colors. Why? Because you know that you see a particular color because that particular color is reflected by that material. If you change the size of the crystals, then that color or the wavelength which is reflected becomes different. Therefore, you have different colors depending on the size of the materials. Next one. Okay, next one. Yeah. Next one. Which I would have like to present. Next one. Next one. Now coming to, because I want to spend some 5 minutes on this, because we have worked on this. You can see that if you look at the amorphous materials like metallic glasses, Dr. Awasthi was talking about anti-corrosion materials. So these metallic glasses are one of the excellent examples which are anti-corrosion, but their dimensions are small, therefore application is hampered, and they are used as anti-corrosion materials in razor blades. They are very good mechanical properties, but as regards the strength, if I give you a ribbon of a metallic glass, it will be in the form of a ribbon, you cannot break it. So mechanical strength is very high. It is higher than even steel. You can see from this graph that if you talk about the different properties like fracture, toughness, strength, they are highest for these amorphous materials. This is due to the fact that there is no grain boundary, and they are amorphous, so there is no grain boundary. So and due to this, there is no corrosion. So if you find a metallic glass ribbon, and it will be shining years after years, even though it contains iron, right? So that another property which is corrosion resistant, I have not shown here, but it is highly corrosion resistant, and its strength is very high. So it is also used as bone implant for any surgery. But again, I am saying because the dimensions in which it is prepared is not very high, so still it's not very cost effective at least. Next one. Yeah, next one. Yeah, these are some of the applications, like in golf club, but also used in joints. Next one. Because it is anti-corrosion resistant, therefore, this is something which I was talking about, the nanocrystallization of metallic glasses by controlled annealing. So these are some of the systems which have been converted into this nanocrystalline materials by controlled annealing. Next one. Yeah. So you can see that this is actually the bright field image of a glass after annealing. So you can see few nanocrystals dispersed in amorphous matrix, and you can see selected area electron diffraction pattern in which these nanocrystals have been characterized, or their phases are identified, and by selected area electron diffraction pattern. Next one. Yeah, next one. Now coming to this high-fold symmetry, you can see that any material which has a two-fold symmetry, because if you rotate it by 180 degree, symmetry may be, the minimum symmetry is that. Then after that, you can see that on this picture, right hand side, you have a kind of 5-fold symmetry. So there are 5 axes about which the system is symmetrical. This is basically micro electron diffraction pattern, that is the diffraction pattern from single crystal, and you find that this 5-fold symmetry in this particular system exists. This comes under the category of quasi-crystals. Next one. So, again, next one. Next one. So what are the, this is the man, Dan Shechtman, in 2011, he got the Nobel Prize in chemistry for the discovery of quasi-crystals. Yeah, next one. Next one. Yeah. So what is the advantage, or what is the difference? Here, broadly, we can classify a crystal, a quasi-crystal, and an amorphous material. Crystal, anyway, we know that if you talk about long range order, yes, there is long range order. Periodicity, also yes. And if you talk about amorphous materials, there is neither long range order nor periodicity. But if you talk about quasi-crystals, then they have long range order but no periodicity. So these are some of the exotic materials, quasi-crystals. So if you can, next one. So we can have these quasi-crystals, and we can have nano quasi-crystals. Next one. Next one. Yeah. All are, you can see this is an example of an amorphous material which is annealed, and after annealing you can see this image of this symmetry. Next one. This is a theoretical study. Well, I will skip this. Next one. This is again a molecular dynamics simulation. Next one, of the quasi-crystalline phase. We call it quasi-crystalline phase in amorphous materials. Next one. Next one. Yeah, these are some phases. Next one. So, finally we can say that there is plenty of room for research on materials at nano scale. Next one. Thank you.
Thank you. Any material which you synthesize, if you control the rate of heating, you can lead to the quasi-crystal stage, and that is what is in nano order. Couple of atoms are organized, and again they are not periodic, perhaps in quasi-crystal, or the periodicity is still there.
No, periodicity is not there, but
Not there. Yeah, yeah.
Actually, the applications are non-stick cookwares.
Corrosive.
So non-stick cookwares, you have quasi-crystalline.
Yes, there is removal of grain boundary.
Yeah, that's right.
Yeah, you have given a very good example of body implant, and I recently got that body implanted by body knee replacement. Perhaps it could be the same material you are talking about.
But biocompatibility is again a question.
Okay.
All the systems cannot be biocompatible, and they have to conform to certain requirements. So, but
Are there any quick questions from the student audience? I will prefer if there are. Did you follow the topic or the subjects? the quasi-crystal. Okay? There is a short-range ordering, long-range ordering is not there. Few atoms are organized. Okay? And that is what is a very interesting aspect in nanomaterial.
So I hope I have at least not tortured what Ritu says about my classes.
Okay, thank you, Arun Pratap. Thank you so much.
Thank you.
I'd like to invite ये काम में लेते हैं, and they are having frequency of the order of gigahertz. Alright? But the power is limited, about 600 watt, 800 watt, or 1 kilowatt maximum, 1000 watt. But perhaps Professor Joshi talks about kilowatts and megawatts devices and the material science related with the high power devices. Okay, so we are eager to listen to Professor Joshi.
Namaskar, that's what you address here. Namaskar to all of you. Honorable Chairman and the faculty members and their students. You have already heard about the nanotechnology and quasi-crystals. I take you to the different world of microwaves. You may not be familiar with microwave devices, but you are users of microwaves and you have a course in microwaves. You agree with me or?
Yes.
Yes, sir.
Okay. So, so first of all, I thank the organizers, particularly Dr. Ritu and Dr. Bhargava, and Dr. Sharma, particularly I'm acquainted with long back, for inviting me to this place. As I told you, the microwaves range from, conventionally we say 3 gigahertz, to 30 gigahertz, we call them microwaves, because their wavelength is in centimeters. Once we go beyond 30 gigahertz, the wavelength falls in millimeters, so we call them millimeter waves up to 300 gigahertz. After 300 gigahertz, their wavelength goes below 1 sub-millimeter. That's why they are known as sub-millimeter waves, or beyond that, terahertz wave. But all are, otherwise the principle is same. The phenomena is same. All are RF waves, moving with the velocity of speed. जोर से बोलिए. Okay, right. But the problem actually here is actually all throughout from 3 gigahertz to 1000 gigahertz or 12 gigahertz, you cannot communicate. There are certain pockets. What is the problem actually? In atmosphere there is a lot of atmospheric attenuation, mostly water vapors, so that your signal get attenuated. So the first pocket in which you can use them is up to 30 gigahertz, where you can communicate. After that there is another window, a certain one with 45 gigahertz. Then another window at 65 gigahertz, then at 95 gigahertz and so on. So there are certain pockets within only you can communicate, you can send your signal, whatsoever you can do. This is about the different bands, and for user, certain bands are allocated. Radar people will have certain band, ISM they have certain bands, for industrial applications certain bands, for medical applications certain bands. Like so, their frequency allocated. Of your own, you cannot choose the frequency band for any application. And as regards the applications of these devices, first and foremost it is in the strategic sector. The strategic sectors almost around the globe, situation is same. 60 to 65% or even more than that goes to strategic sector, like the radar for detecting the enemy's airplane, or jamming, which is known as sometimes you see their cell phones are jammed if there is disturbance in the society. Similarly, your radar station can be jammed. That depends on how superior you are. That's why nowadays war hai, it is the electronic warfare. It's not that purani war nahi hai, gun lekar ke chale gaye. It's electronic warfare. So it depends how much superior, sophisticated technology you have. So that type of is there. So the second application is the communication sector. Communication sector, you see your all ground communication or communication through troposphere, communication through ionosphere, or communication beyond that is again all communication. This is TV. You see the satellites are there, and where they are. Any idea where they are? Which altitude they are? The satellites.
35,786.
Why they are there? What the benefit of using them there? Because they are geostationary. Because once the satellite is there, its relative speed to the Earth is same. So if it is looking at Delhi, every time he will be looking at the Delhi because both are moving, relatively they are moving at the same speed. Then the next application is industrial applications. You all are familiar with in the cooking kitchen you have the microwaves oven. So that is one industrial applications, and that is only very popular in our country. There are other industrial applications wherever you want to remove moisture, you use microwaves because they are environmental friendly, they are more efficient, but they requires a lot of expenditure to set up those things. So in our country, certain tea industries are using these microwaves for drying tea leaves. And some medical applications are being done by Samir in Mumbai for particularly for the hospital waste management, all these things they are doing some. And then there are some scientific applications for heating of the plasma, accelerators, and biomedical applications for treatment of cancer, etc. So these are a number of applications which are with you, and you all have your cell phone in your pockets. Again, that is microwaves, but the power requirement is very low. What about order of power? It's a milliwatt. Okay. Whereas for this strategic applications, you need a power of the range of megawatts or gigawatts also. So I'll just give you, because limited time, I may not go to all the slides, but I have time actually. So I have already been introduced. After my superannuation in 2006, I joined that place in 1968.